Welcome to the deep dive. Today, we're taking a plunge into nuclear chemistry, a topic that might sound complex, but really touches our lives directly, especially when we talk about health and, life sciences. Okay, maybe let's start with a real-world situation. Imagine Simone, she's at her doctor's, concerned about high cholesterol. The doctor suggests a cardiac stress test, but a specific kind, a nuclear stress test. Our source material actually gives a great picture here. Simone meets Pauline, the radiation technologist.
Right, and Pauline explains she'll be injecting a radioactive dye, thallium-201.
Exactly. And the goal is to get these incredibly sharp images of Simone's heart muscle, right? Showing blood flow when she's resting and under stress.
It's really quite clever how it works. Pauline would explain that this thallium-201, it acts like a tracer. Once it's in the bloodstream, it lets them see the blood flow. They can pinpoint any areas maybe where the heart muscle is damaged.
So if there's a blockage, less of that tracer gets there.
Precisely. Less of the radioisotope accumulates in those spots. And that shows up as a cold spot on the scan images. It gives the doctor really crucial diagnostic information.
And this is where Simone, and probably a lot of us listening, would get a bit nervous. Radioactive dye. But Pauline explains the safety aspects, mentioning the half-life of thallium-201.
It was about 3 days for thallium-201. She'd reassure Simone that after, say, 4 half-lives, the radiation level becomes almost negligible, decays into mercury-201, releasing X-ray-like energy that the scanner picks up.
It's pretty amazing, isn't it, how this precise atomic process is used for such critical health information. And really, that's our mission today. We're diving deep into the core ideas of nuclear chemistry, pulling specifically from the textbook chemistry. An Introduction to General Organic and Biological Chemistry by Timberlake. We want to pull out the key insights, connect the science to how it actually applies in, well, health and everyday life.
Consider this your shortcut to getting the important stuff.
Yeah, the stuff that sticks with you.
And it's crucial because, as you'll see, these concepts, they literally power some of our most advanced medical tools, both for diagnosis and treatment. And believe it or not, they even help us figure out how old the Earth is.
So it's not just lab coats and equations.
Not at all. It's about the fundamental forces shaping our world, our health, everything.
Okay, so let's start right at the beginning then. When we talk about nuclear chemistry, what is natural radioactivity? It sounds, well, powerful, maybe a bit scary, but you're saying it's natural, all around us.
That's a great starting point. Most elements up to atomic number 19, think calcium and below, they generally have stable nuclei. But once you get to atomic number 20 and higher, things change.
How so?
Well, elements often have isotopes, versions of the atom with unstable nuclei. These are radioactive. Essentially, the forces holding the nucleus together are a bit out of balance. So to become more stable, they spontaneously release tiny bits of energy or particles. We call that release radiation.
And some elements are always radioactive.
Yes. Anything with an atomic number 93 or higher, like plutonium or americium, they only exist as radioactive isotopes. And interestingly, they have to be produced artificially. They don't occur naturally in significant amounts anymore.
Okay, so these small particles of energy, that's the radiation. But the word radiation often just sounds like one big, dangerous thing. It sounds like it's more complicated than that. Are there different kinds?
Absolutely. And understanding the differences is key, especially for medicine. First up, you have alpha particles. Think of them maybe like tiny cannonballs, relatively heavy, slow.
Cannonballs, okay.
Yeah, they're identical to a helium nucleus that's 2 protons, 2 neutrons. So they have a positive charge, a charge of 2 plus what? Its symbol is eco.
Got it. Heavy, positive. What's next?
Then there's the beta particle, symbol part.
Yeah.
This one's essentially a high-energy electron, much, much lighter than an alpha particle and faster. It carries a negative charge.
An electron. Where does it come from?
It actually forms inside the nucleus when a neutron suddenly changes into a proton and an electron. The electron gets ejected at high speed. That's the beta particle.
Huh. Okay. And I think I saw something about a positron.
Yes, the positron. Bi a plus, bis. It's fascinating. It's like the beta particle's twin, but with a positive charge, 1 plus. Same tiny mass, opposite charge. It's an example of what we call antimatter.
Antimatter, wow.
Yeah, and when a positron meets an electron, they annihilate each other, releasing pure energy.
And the last one, the one we hear about most maybe, gamma rays.
Right, gamma rays.
Yeah.
These aren't particles in the same sense. They're pure energy, high-energy electromagnetic radiation. No mass, no charge, just energy.
Yeah.
They're often released alongside alpha or beta particles when a nucleus rearranges itself into a more stable, lower-energy state.
So different types, different properties.
Exactly. And knowing these differences is crucial for using them safely in medicine and, well, for protecting ourselves.
That leads right into the next big question, probably on your mind as you listen. If this radiation is around, how does it affect us? And how do we stay safe?
Well, the types we've discussed are called ionizing radiation. That means they have enough energy to knock electrons right off molecules in your body. This creates unstable ions.
And that's bad.
It can be. If these ions mess with water molecules, for example, it can trigger unwanted chemical reactions. Now, the cells most susceptible to damage are the ones dividing rapidly. Think bone marrow, skin, reproductive organs, the lining of your intestines, and importantly, all the cells in growing children.
But wait, isn't that why radiation is used for cancer treatment?
Exactly. That rapid division is the cancer cell's vulnerability. Radiation preferentially damages those fast-dividing cancer cells. Cells that don't divide much, like nerve cells, muscle cells, adult bone cells, are much less sensitive.
Okay, that makes sense. So, protection. You mentioned 3 rules.
3 golden rules: shielding, time, and distance. For shielding, it depends on the type. Alpha particles. Heavy, slow. They only travel a few centimeters in air. Paper, clothes, even the outer layer of your skin stops them easily.
So not dangerous from the outside.
Generally, no, but, and this is a big but, if you inhale or swallow something emitting alpha particles, they can do serious damage inside because they deposit all their energy in a tiny area.
Ah, okay. What about beta?
Beta particles travel further, maybe a few meters in air. They can get a few millimeters into your tissue, so you need heavier clothing, lab coats, gloves.
And gamma, the pure energy ones.
Those are the tricky ones. Gamma rays travel long distances and penetrate deep. You need dense stuff to block them, thick concrete or lead. That's why X-ray techs stand behind lead shields.
Right, so shielding is key. What about time and distance?
Simple principles, really. Time. Minimize how long you spend near a radioactive source. Double the time, double the exposure. Distance. Get further away. Radiation intensity drops off super fast with distance. Double your distance, and the intensity you receive drops to just 1/4.
So stay back, don't linger.
That's the essence. And these principles are exactly what informs the safety protocols for technologists like Pauli, making sure everyone's safe.
Okay, so we understand the types and the safety. Now, let's get into how elements actually change. You mentioned nuclear reactions, atoms transforming. That sounds, well, almost like alchemy.
It does feel a bit like that.
Yeah.
In radioactive decay, an unstable nucleus just spontaneously breaks down, spitting out radiation. And here's the part that would have amazed early chemists like Dalton. The atom can literally become an atom of a different element.
Seriously?
Absolutely. The key is balancing the equation. In nuclear equation, the total mass numbers, protons plus neutrons, and the total atomic numbers, protons, have to be the same on both sides of the arrow. But the identity of the element, defined by the atomic number, can change.
Mind blown. Okay, give me some examples. How does this work?
Okay, take alpha decay. The nucleus kicks out an alpha particle. 2 protons, 2 neutrons. So the remaining nucleus has its mass number decreased by 4 and its atomic number decreased by 2. A classic case is uranium-238 decaying into thorium-234.
Uranium becomes thorium.
Exactly. Another example, americium-241, used in many smoke detectors, undergoes alpha decay.
Okay. What about beta decay?
In beta decay, remember, a neutron turns into a proton and an electron. The electron, beta particle, gets ejected. So the mass number doesn't change. Losing a neutron, gaining a proton cancels out, but the atomic number goes up by 1 because there's 1 more proton.
So an element turns into the next one on the periodic table.
Pretty much. A carbon-14, for instance, undergoes beta decay to become nitrogen-14. And linking this to health, this process is involved with radon gas. Radium-226 in the soil decays by alpha decay into radon-222 gas. That radon gas then undergoes beta decay, leading to polonium-218, which is unfortunately a known lung carcinogen.
That's why radon testing in homes is important.
Very important. The EPA has guidelines recommending levels shouldn't exceed 4 picocuries per liter.
Right. Okay, what about positron emission, the antimatter one?
Similar outcome to beta decay in terms of mass number. It stays the same, but the atomic number goes down by 1. Here, a proton essentially turns into a neutron and ejects a positron. So, for example, aluminum-24 decays into magnesium-24.
And gamma emission, you said that's just energy.
Exactly. No change in mass number or atomic number. The nucleus just releases a burst of gamma energy to settle into a more stable state. Technetium-99 meter, that tracer used in Simone's scan, is a perfect example. It's primarily a gamma emitter, releasing energy to become more stable, technetium-99.
And you mentioned some of these are made artificially.
Yes, many of the radioisotopes most useful in medicine aren't abundant naturally. We make them by bombarding stable atoms with high-speed particles, neutrons, protons, alpha particles, in things like nuclear reactors or particle accelerators.
Like the technetium-99 meter.
Precisely. It's often produced from molybdenum-99. And it's so useful because those gamma rays it emits pass right through the body to the detector, giving a clear picture without depositing a lot of damaging energy along the way.
Okay, so we have these different types of decay transforming elements,
Mm.
but how do we actually detect this radiation? It's invisible, right?
Mostly invisible, yes. One common tool is the Geiger counter. You've probably heard the clicking sound.
Yeah, in movies usually.
Yes. It's basically a tube filled with gas. When radiation zips through, it knocks the electrons off the gas atoms, ionizing them. This creates charged particles, allowing a brief electrical current to flow. Each pulse of current makes that click sound and moves a needle or updates a digital display.
So it counts the radiation events, but how do we measure the amount or the effect? I hear different units mentioned, Curies, rads, rems. It gets confusing.
It can be, but each unit tells us something different and important.
Wow.
First, there's activity. This measures how many radioactive atoms are decaying per second. The units are the Curie, named after Marie Curie,
Yeah.
or the Becquerel, BQ. It's about the rate of decay.
Okay, how fast it's happening.
Exactly. Then there's absorbed dose. This measures how much energy the radiation actually deposits in material, like your body tissue. The units here are the rad, radiation absorbed dose, or the gray. Okay, it's about energy absorbed per kilogram of tissue.
So how much energy gets dumped into you?
Right. But different types of radiation cause different amounts of biological damage, even if they deposit the same amount of energy. That's where the biological effect or equivalent dose comes in. It adjusts the absorbed dose based on the radiation type.
How does that work?
We use a quality factor. Beta and gamma rays have a factor of 1. But alpha particles, because they do so much damage in a short path, have a factor of 20. So 1 rad of alpha radiation causes 20 times the biological damage as 1 rad of gamma radiation if it's inside you. The units for this biological effect are the rem, Röntgen equivalent man, or the sievert, SV.
So REMs and sieverts tell you the actual biological risks.
They give the best overall picture of potential harm, yes. Understanding all 3 activity, absorbed dose, and equivalent dose gives a complete picture of radiation's impact.
And this understanding has some maybe surprising applications. Like I read something about radiation in food. That sounds odd.
It does initially, but it's actually a very useful safety measure.
Yeah.
Low doses of gamma rays, often from cobalt-60 or cesium-137, are used to irradiate certain foods to kill harmful bacteria like Salmonella or E. coli. It can also destroy insects, molds, yeasts, and extend the shelf life of things like strawberries, pork, beef, poultry.
That doesn't make the food radioactive.
Absolutely not. That's the crucial point. The food passes through the radiation field, but it never touches the radioactive source itself. The gamma rays kill the microbes, but the food itself does not become radioactive at all. It's used for astronaut food, food for hospital patients with compromised immune systems.
Right.
It's about safety.
Okay, that's reassuring. And what about just everyday radiation exposure? Are we constantly exposed?
We are. There's natural background radiation everywhere. Potassium-40 and carbon-14 are naturally radioactive isotopes present in our own bodies. Radon-222 gas comes from the decay of uranium in soil and rocks and can accumulate in buildings.
So inside and outside?
Yep. Plus, we get radiation from cosmic rays coming from space, more if you live at high altitude or fly often. And of course, medical procedures like X-rays or CT scans contribute. On average in the U.S., a person gets about 3.6 millisieverts, MSV, per year from all sources combined.
And what happens if you get a much larger dose? We hear about radiation sickness.
Right. The effects depend heavily on the dose. Below about 0.25 sieverts, 250 millisieverts, effects are usually undetectable. Around 1 day, you might see a temporary drop in white blood cell count. Above that, symptoms like nausea, vomiting, fatigue can appear. Higher doses, above 3 SV, can lead to hair loss, diarrhea, increased risk of infection. Around 5 SCV is considered the LD50, the lethal dose for about 50% of the population within 30 days if untreated.
That's serious.
It is. That's why people working regularly with radiation, like hospital staff or nuclear plant workers, wear dosimeters, little badges that measure their accumulated dose to ensure they stay well below safe limits.
Okay, this brings us back perfectly to Simone's question right at the start. This concept of half-life. What exactly is it?
It's a really fundamental concept in nuclear chemistry. The half-life of a specific radioisotope is simply the time it takes for half of the radioactive atoms in the given sample to decay into something else, usually a more stable atom.
Half the atoms just disappear.
Not disappear, they transform. Let's use iodine-131 again. It has a half-life of about 8 days. If you start with, say, 20 milligrams of I-131, after 8 days, you'll only have 10 milligrams left.
And after another 8 days.
You'll have half of the remaining 10 milligrams, so 5 milligrams. Then after another 8 days, 2.5 milligrams, and so on. It decreases by half repeatedly over each half-life period.
So why do some have short half-lives like hours or days, while others last for thousands or even billions of years? What's the significance?
That variation is huge and incredibly important. For medical uses, like the technetium-99 meters in Simone's scan, half-life 6 hours, or iodine-131, 8 days, we deliberately choose isotopes with short half-lives.
Why short?
Because you want the radioactive material to do its job, allow imaging or deliver therapy, and then disappear from the patient's body quickly to minimize their overall radiation dose. Once the scan is done, you want that radiation gone.
Makes sense. And the long ones.
Contrast that with naturally occurring isotopes like carbon-14, half-life 5,730 years, or uranium-238, half-life about 4.5 billion years. These decay incredibly slowly, producing low levels of radiation over immense stretches of time. They're part of our natural background radiation.
And that long half-life of carbon-14, that's used for dating ancient things, right? Carbon dating.
Exactly. It's one of the most brilliant applications of half-life. Carbon-14 is constantly being made in the upper atmosphere when cosmic rays hit nitrogen. Plants absorb it as CO2. Animals eat plants, so all living things have a certain steady ratio of carbon-14 to stable carbon-12.
Okay.
But when an organism dies, it stops taking in new carbon. The carbon-14 it already contains just starts decaying away, with its 5,730-year half-life. So scientists can measure the remaining ratio of C14 to C12 in an ancient organic sample like wood, bone, cloth, and calculate how long ago it died.
They're the Dead Sea Scrolls.
Precisely. Carbon dating helped confirm they were about 2,000 years old, matching historical estimates. It works well for things up to maybe 50,000 years old.
And for things even older, like rocks. You mentioned uranium.
Right. For really ancient things, like geological formations or even dating the Earth itself, we use isotopes with much longer half-lives. Uranium-238 dating is key here. It decays through a long series of steps, eventually into stable lead-206, with that incredibly long half-life of 4.5 billion years.
So you measure the uranium and the lead.
Geologists measure the precise ratio of remaining U-238 to the accumulated Pb-206 in rock samples. That ratio acts like a clock, telling them when the rock solidified. It's how we know the oldest rocks on Earth and rocks brought back from the moon are billions of years old. It's truly dating on a cosmic scale. So let's circle back and really focus on these medical applications. The core idea, as we touched on, is pretty elegant. Your body's cells often can't tell the difference between a radioactive isotope and its stable counterpart.
Like the iodine-131 and regular iodine?
Exactly. So we can design radioisotopes that we know will naturally travel to and concentrate in specific organs or tissues. Then, the radiation they emit acts like a beacon. We use detectors outside the body to pick up that radiation.
Which leads to scans.
Right. Scanners detect the gamma rays coming from the radioisotope inside the patient. Computers then build up an image showing where the isotope is accumulated. This can reveal tumors, blood clots, check organ function, all sorts of things.
And the thyroid scan with I-131 is a classic example.
It really is. A patient drinks a small amount of solution containing I-131. The thyroid gland naturally takes up iodine. The scanner then measures how much I-131 the thyroid absorbs. Too much uptake could mean hyperthyroidism. Too little, hypothyroidism. And as we mentioned, higher doses of I-131 can actually be used therapeutically to destroy overactive or cancerous thyroid tissue.
What about PET scans? Positron emission tomography, that sounds advanced.
It is quite sophisticated. PET scans use isotopes that emit positrons, remember, the antimatter electrons. Things like carbon-11, oxygen-15, fluorine-18, all with very short half-lives.
And the positrons do what?
When a positron is emitted inside the body, it almost immediately bumps into an electron. They annihilate each other, releasing two gamma rays that shoot off in opposite directions. The PE scanner detects these pairs of gamma rays. Computers then reconstruct a detailed 3D image showing where the annihilation events happened.
What kind of things can PT scans show?
They're incredibly powerful for studying metabolic activity. They can show brain function, blood flow, how tissues are using glucose. Very useful for detecting cancer, studying heart disease, and neurological disorders.
Now, it's probably good to quickly mention that not all advanced imaging uses radiation, right? Just for context.
That's a very important point. Computed tomography, or CT scans, use X-rays, which are ionizing radiation, but they work differently. Multiple X-ray beams pass through the body from different angles, and detectors measure how much gets through. A computer then builds a cross-sectional image based on tissue densities. great for spotting tumors, hemorrhages, bone issues.
And MRI.
Magnetic resonance imaging, MRI, is completely different. No ionizing radiation at all. It uses powerful magnets and radio waves to interact with hydrogen atoms in your body's water molecules. Different tissues respond differently, allowing computers to create incredibly detailed images, especially of soft tissues like the brain, muscles, ligaments. It's generally considered the least invasive imaging method.
Good to have that comparison. But back to radiation therapy. You mentioned brachytherapy. Internal radiation.
Yes, brachytherapy literally means short-distance therapy. The idea is to place the radioactive source directly inside or very close to the tumor. This delivers a very high, concentrated dose of radiation right where it's needed, while minimizing the dose, and therefore the damage, to the surrounding healthy tissues.
How is it done? Implanting things.
There are two main ways. Permanent brachytherapy is often used for prostate cancer. Tiny radioactive seeds, smaller than a grain of rice, containing isotopes like iodine-125, palladium-103, or cesium-131, are implanted directly into the prostate gland.
They just stay there.
Yes. They emit gamma rays with relatively short half-lives, gradually destroying the cancer cells over weeks or months. Most of the radiation is gone within months, but the tiny inactive seeds remain harmlessly.
Okay. And the other type?
Temporary brachytherapy. In this case, hollow needles or catheters are placed in or near the tumor. Then, a highly radioactive source, often iridium-192, is inserted into those needles for a short specific time, maybe just 5 to 10 minutes, delivering a powerful dose quickly. Then, the source and the needles are completely removed.
A higher dose, shorter time, nothing left behind.
Exactly. It's used for various cancers, including prostate and breast cancer. The key advantage for both types is targeting the radiation precisely where it's needed.
Okay, shifting gears one last time, let's talk about the sheer power locked inside the nucleus. Fission and fusion. Starting with fission.
Right. This was the huge discovery back in the 1930s. Scientists found that if you hit a uranium-235 nucleus with a neutron, it becomes unstable and splits roughly in half into two smaller nuclei.
And that releases energy.
An immense amount of energy. This is where Einstein's EMC2 really shows its power. Even though only a tiny fraction of the mass is converted, the c-squared part, the speed of light squared, is such a huge number that the energy release is enormous. Fissioning just 1 gram of U-235 releases the same energy as burning about 3 tons of coal.
Wow. And it keeps going, the chain reaction.
That's the key. When the U-235 nucleus splits, it also releases 2 or 3 more neutrons. These neutrons can then hit other U-235 nuclei, causing them to split, releasing more neutrons, which hit more nuclei. It snowballs very quickly into a chain reaction. You need a certain minimum amount, a critical mass of the uranium for this chain reaction to sustain itself.
Which is how nuclear weapons work, uncontrolled, but also power plants controlled.
Exactly. We'll get to power plants in a sec.
Yep.
First, let's quickly touch on nuclear fusion.
The opposite, joining atoms instead of splitting them.
Correct. Fusion involves combining two very light nuclei like isotopes of hydrogen to form a slightly heavier nucleus, like helium. And remarkably, this process releases even more energy per unit of mass than fission does.
More energy? Why aren't we using it then?
The challenge is immense. To get those light nuclei to fuse, you have to overcome the incredibly strong electrical repulsion between their positive charges. This requires temperatures of around 100 million degrees Celsius.
Million degrees.
Yes. That's the kind of temperature found in the core of the sun. Fusion is literally what powers the stars. Our sun fuses about 600 billion kilograms of hydrogen into helium every single second.
Incredible. So fusion power on Earth.
It holds huge promise, potentially vast amounts of energy, with less long-lived radioactive waste than fission. But achieving sustained, controlled fusion at those temperatures is incredibly difficult. We're still very much in the experimental stage, trying to build reactors that can contain that superheated plasma.
So back to what we can control. Nuclear power plants using fission. How do they work?
They use the heat generated by a controlled nuclear fission chain reaction. Inside the reactor core, uranium-235 fuel is used, but it's kept below the critical mass needed for an explosion. Control rods, often made of materials like cadmium or boron that absorb neutrons, are inserted into the core.
To slow things down?
Precisely. By raising or lowering the control rods, operators can control the rate of fission, keeping the reaction steady and preventing it from running away. The intense heat generated boils water, creating steam. That steam then drives turbines connected to generators producing electricity.
Just like a coal or gas plant, but the heat source is nuclear.
Essentially, yes. Nuclear power provides about 20% of the electricity in the U.S., which is significant, and it doesn't produce greenhouse gases during operation.
But there's the waste issue.
That's the major challenge, yes. Fission produces radioactive byproducts, some of which, like plutonium-239, have extremely long half-lives, 24,000 years in the case of Pu-239. Finding safe, secure, long-term storage solutions for this high-level radioactive waste is a critical and ongoing issue for the industry and for society.
What an incredible journey, really, into the heart of the atom. This deep dive looking at nuclear chemistry. It's shown how these fundamental ideas about atoms being stable or unstable, how they decay, how energy is released, they connect directly to things like Simone's life-saving heart scan, but also to the massive power plants that light our cities.
It really is a field where tiny subatomic changes lead to effects on a massive scale, from healing individual cells to powering entire countries. The impacts are just profound.
It really makes you think.
And maybe a final thought for you to consider. As we get better and better at understanding and manipulating these subatomic particles, we're not only finding new ways to diagnose and treat diseases, but we're also grappling with the immense potential and the serious challenges of harnessing nuclear energy for our future.
What other discoveries are waiting out there?
Exactly. What new frontiers might open up as we keep probing deeper into the very heart of matter? It's a fascinating question for the future.
Thank you so much for joining us on this deep dive.
And a warm thank you from the Last Minute Lecture team.